So the last big trend that's enabling this is machine learning protocols that allow us to train as opposed to program a robot. And this is a monumental shift in the way that we interact with robotics, because whereas programming a robot takes a lot of time, a lot of effort, you have to sit down, as I'm sure Bhargav can tell you, writing Python is no joke, and sitting down and actually being able to dictate every single line of code that the robot should follow takes months and weeks. With machine learning, we're able to, instead of programming a new task into the robot, train it on a new skill set. And that allows us to, train it to do new things in hours and days as opposed to weeks and months.
And then using machine learning, we can actually get reflexive information from the robot. So the robot learns the task at hand, and we'll show an example of this a bit later, but it learns the task at hand, and based on what it's supposed to do, it can have reflexive instincts almost. It's really cool. And also with all that data we get and how it performs the task, we can give it continuous improvement based on rewards and punishment.
And it's observing and interacting and learning from the world in real time as it's doing tasks, right? So if it fails, it's going to ask the question, why did it fail? Now that's going to require some human input, right? Because we want to make sure that we keep humans involved in the process, keep their input kind of front and center, so that the machine's not going off the rails, right? But it is at least able to gather that data, make inferences about what went wrong, and make sure that it doesn't happen again, basically.
So here's an example of a system. It's called UMI, so it stands for Universal Manipulation Interface. So basically what you see here is us doing the training process. So you can see this is the gripper. We have it 3D printed right here. On top is a GoPro. So that GoPro is basically recording us picking and placing the teacup in a saucer in different angles, different orientations, different lighting conditions, different backgrounds. And you can also notice that there are different teacups as well. So what we do, we use this as it's called imitation learning, and I'll get into that a bit more later, but this is kind of like our training data. So we are the experts. We constantly do the same task over and over again, save the videos on the GoPro, and then we can deploy it onto a robot, which does the same exact thing. You want to go to
Yeah. So for example, one thing to point out here, just as we're kind of talking about the difference between programming and training, to program a robot to pick up each of these different teacups, we would, for example, need to know the exact diameter of each different teacup. And that's not always the case, right? And so to build a robot that's actually able to interact with a whole universe of teacups, not just one particular type of teacup, we needed to, first of all, be able to recognize that that's a teacup, and that's the vision component. We need to have the tactile awareness to know how hard to grip the teacup so that we don't smash it. And we also have to have the audio awareness to be able to receive the commands to say, hey, go clean off the table. And you'll see in a second here that we can actually send those actions straight to any robot in the world.
So you'll notice here that they actually just pull up the robot. It's not in like a fixed coordinate system. They just move it on some wheels. They start the policy, and now the robot has the exact same end effector gripper that we had in our UMI. So it sees the teacup in front of it. Again, you'll notice that it's a different teacup in a different position. It knows the task at hand. So it's to pick up the teacup, place it on the saucer in a certain orientation. And now as we move it, it again, kind of like a reflexive motion, will pick up the teacup and place it in the saucer. So nowhere here have we programmed it to go to certain XYZ coordinates. Yes?
You have to have the same end effector
Yeah.
to be able to use?
For this method, yes, because it works on using, basically you'll see some Ruko markers here. So it uses the exact same gripper mechanism. So from the viewpoint of the GoPro, this tells you how hard to grip the object in our training data. So it uses all that data, including how much we're like, how much pressure we're giving to the gripper. That way we can deploy the same gripper pressure on the robot.
And this is just one example. There are systems that integrate, more complex technologies to, be able to do the same task with different types of grippers. But it's one of the things that we always look at, which is what is the solution that is least complex that still delivers that business value? And so just by centralizing and standardizing the gripper size, we're able to avoid a lot of the complexity that might come with, other input devices there. Was there another question?
Yes, so if I understand correctly, by when the lady was doing picking it up, she is measuring the distance that the arms have to move in order not to put too much pressure on it. Is that correct?
So actually what she's doing is what the machine learning model is doing is measuring the distance from the GoPro itself, which is mounted here, to the end effector. And it centralizes the object that you're trying to pick up in the frame and does frame by frame computer vision to determine, okay, I need to get closer to that object. Boom, I'm exactly where I was when the training was happening.
So, yeah, good. So can it take, now, will you put a larger object or a smaller object? Could it pick it up then to the right pressure?
Or you would take that cup and put it on its side.
Excuse me,
So if we trained it,
excuse me, sorry, you asked my question before you go to answer.
Absolutely, yeah. So, there are obviously going to be mechanical constraints. If the object is too large for the gripper itself, that would not be compatible here. But for example, if you shrunk the teacup down substantially smaller and wanted to pick it up and it was still within this kind of framework here, it would probably do almost as well. It would be a little bit thrown off because the proportions would be a little bit different. But the solution to that is gather more data. So by learning from the experience as it's having it, for example, I guess what I would say is the first time it sees that tiny teacup, it might have some trouble. The 10th time it sees that tiny teacup, we're going to be in business. Does that answer your question? I'm sorry, I want to make sure. Thank you. I appreciate it.
So then I guess moving on to, you had those different types of teacups and that sort of, but the same thing. So if I was to put that teacup on its side, is it going to look at it and go, I don't see that as a teacup, I'm not able to react?
It would see that it's a teacup and orient the gripper to be in the same orientation and then pick it up and place it back on
I
the
do want to
saucer.
reiterate that this is imitation learning. So it's learning through imitation. So as long as it has been trained on those situations, it will know how to deal with that situation. So if it was on its side and we had a couple of picks where it knows what to do in that situation, then it can be on its side. It could be like on its side over here. It could be rolling around and it still know how to do it. But we need to make sure that through imitation, it knows what to do.
That's a good point because that's also how we make sure that the solution stays on the rails and that we're doing what we want it to do. For example, we wouldn't want it to kind of spontaneously pick up the teacup and throw it in the trash, right? So we want to make sure that it's doing exactly what it's doing in the training protocol that's kind of gathered data from the expert. Yeah, go ahead.
Are you also using the data at the inference time to retrain?
What's that?
Are you using the data from the inference time to retrain also?
You could, yeah.
No, but are you doing that? That's what I'm asking.
In this example that's on the screen right now, we're not, just because it's kind of in a lab environment. But for real world deployments, we absolutely gather all of that data. Now, I will say that we don't necessarily feed all of that data just directly back into a machine learning algorithm. That's a crucial step where we say that humans need to have some involvement so that we can understand what is an error and what's an anomaly. I'll give you a really good example. We work in a metal shop in Georgia, helping them with a lot of processes. And one of the things that we noticed in our data logs is that almost every Tuesday at like 2 o'clock, errors went through the roof and, failure rates skyrocketed and things were going wrong. And it was like clockwork every Tuesday at 2 o'clock. And we could not figure out what technological failure was creating this outcome until we went down there and looked at it ourselves. And what we saw is that on Tuesdays, the taco truck comes to the parking lot and they open the large garage bay door, which floods the scene with a bunch of additional light. And we had not gathered data for the robot to perform in those environments, right? And so we wouldn't necessarily want the robot to be guessing at what changed and what needs to be improved. We would want a human involved to say, hey, this is the environment that you need to adapt to, and these are the specific changes that you need to perform to do better. Because it doesn't necessarily always understand what is better, right? I think there was another question. Sorry, go ahead.
So to train in that example, do you actually have to go train with, actually do the training with more light, or can you just take the video you already recorded, put it through photo editing or whatever, just dial the brightness and retrain? Will that work sufficiently?
Yeah, I mean, those are all different ways to increase our training data. Yeah, we could increase our light and actually take pictures and do it ourselves. it is a lot of effort to do that, but like you mentioned, there is data augmentation where we can just increase the exposure, or we can just like add artificial light to pictures and add artificial shadows, and that would also be used for training. Yeah.
And the real answer is both. You know, we want a healthy amount of natural data in the pipeline, but in order to train things faster and, you know, move things forward a bit faster, we frequently do use synthetic data to amplify our data sets. So we'll take, for example, just on a, you know, kind of a still image-based model, if we have 500 images, what we'll do is simulate different lighting conditions exactly like you mentioned, simulate pixel degradation, simulate cable breaks, and, you know, all of those different things that we can kind of augment the data synthetically to simulate, and combine all of that into a combined training data set.
Yeah. I think we should continue moving forward. We'll take the questions at the end if that's okay.
But as we were talking about, there's really three kind of main points to the training and machine learning component. It's expert demonstration, data gathering, and then sending that data through a machine learning pipeline. The thing that I want to underscore here, though, is that while we talk a lot about autonomous machines, what the real key here is to keep humans in the loop. Because as always, we want to have kind of expert, you know, demonstrators that actually understand what they're doing. We want to have master painters, master welders, you know, folks that are really experts in their field. Put a device like this in their hands so that we can take advantage of that hard-won expertise, gather it into the data set, and then deploy it to a robot so that that robot's able to, you know, not have to learn from the 40 years of experience that it took that person to get so good at that task. So all of these kind of three trends combine to create a circumstance where these robots are able to not only be more responsive to external conditions, be more easily instructable and reprogrammable, but conquer unstructured environments. And this is really the key frontier that is kind of the blocker for a lot of robotics adoption, is that it's very difficult to take the same technology that works in a lab environment and deploy it into a real world production environment. Manufacturing settings are notoriously dusty, and you know the cleanest shop I've ever been in still has a lot of sawdust on the floor, right? And so there are conditions that you can't control that they still need to be able to adapt to and work with. Logistics, for example, you know, you're always going to have variety in how the packages are presented, how the material is actually packaged. You know, for example, a cellophane bag is impossible to create as a structured item there. Likewise with healthcare, and then a big one that we're really excited about is agriculture as well. So it's interesting to talk about all of these things in a lab environment, but like I said, the real frontier is putting these out in the real world. And there's one that I'm super excited about, which is this company, Agility Robotics. They do make a humanoid, but I will say it's one of my favorite humanoids because it prioritizes function over form. So you'll notice as we watch this video that it doesn't actually look like a lot of other humanoids. If you look at the robot in the scene, the legs are kind of backwards. The arms don't look totally like arms. The hands don't really look like hands. It still looks like a robot and functions like a robot, but has all of the benefits of humanoids being able to conquer unstructured environments. And they've had some news recently, which is basically they're partnering with Amazon in what is, I think, a perfect use case for humanoids, which is package delivery. I could almost not imagine a more unstructured environment than the exterior of my own house, particularly because I live in a construction zone right now. But you know, you're always going to have the kid that left the bike in the driveway. You're always going to have the dog that's you know, kind of attacking the mailman. Although in this case it's a robotic mailman, I don't think it'll make a difference. But what Amazon is doing is basically using a fleet of autonomous vehicles combined with these digit robots that you see here. You can see the backwards legs that I was talking about. And using them to carry packages to the doors of everyday customers. This is especially exciting because what Digit's also done is created a new safety standard for bipedal robots that enables them to actually get out in the world and be in our spaces without you know, necessarily causing danger or harm to anybody. We have a great interview with Melanie Weiss, the Chief Products Officer of Agility Robots. I'd encourage everybody to check it out. She gets into the nitty-gritty details of exactly, you know, what design choices were made, why the legs are backwards, you know, why the hands don't look like hands, and all of that great stuff.
So here's another demo that we like to show. Is this one's by Figure, if anyone knows about that company, and these are their new Helix robots.
So
I'll just yeah.
Yeah, this is one that we like a lot because it shows a couple of different input varieties here. Unfortunately, we don't have audio, but what is happening in the screen here is basically this man is unloading things onto the table and then just saying the words to the robots, look at these items, figure out where they should go, and put them away. And it combines a couple of different things here, one being a vision action model, which enables the robot to know exactly what it's looking at, understand how to interact with it, and put it in its place. Another one is this kind of idea of collaborative robots, right? Where they're working together to accomplish a shared mission. And there's a lot of technical things under the hood that's driving that as well.
This is the perfect example of sensory perception, what we talked about earlier. So these robots do utilize the sense of sight, sound, and touch. So like Tony mentioned earlier, they have microphones. The man in the video told these robots, hey, look at these objects you've never seen before and organize them in this kitchen. They also have a big camera on their forehead and a couple other cameras around them so they can actually see the world around them. And then for tactility, the hand end effectors that you see grabbing the actual objects have force torque sensors in them. So that's how they can grab such fragile objects like the ketchup bottle and the cookies without actually destroying them.
And it's interesting to watch. You'll notice a lot of contrast between this approach to humanoid robots compared to Agility's approach, where this looks a lot more human in some ways, but a lot less human in other ways. By a show of hands, who would classify this as creepy? Just about everybody in the room, right? Who would say that the green digits that we saw a moment ago are creepy? Fewer people, still some, right? And there's this idea called the uncanny valley in robotics, where when something looks close enough to human to kind of trick our brains into thinking it might be for a moment, but misses the mark on a few key characteristics, our intrinsic response is to be a little bit afraid of it and a little bit wary of it. And so one of the ways that you can avoid this is by leaning into this kind of form factor that we saw with Agility, where it's human enough to interact in human environments, but not human enough that it kind of freaks us out a little bit. Now, it's also important to note that this is not just happening in a lab environment. These robots are actually in warehouses being put to work every day. Now, this is another good example of kind of task-oriented robotics versus humans. Now, one of the arguments that we hear a lot is that you have to have a humanoid robot for every task. Well, what I would say here is we have 4 limbs on the screen, but I only see 2 of them being used here, right? And so for a lot of businesses that are thinking about automation, my question to them is, why are you paying for 2 limbs that you're not using? And so it really underscores this idea that when we think about automation and Industry 4.0 and how to actually drive adoption, it's always about choosing the right tool for the job, configuring that tool correctly, and putting it to work on something that actually brings value to the business.
So even though this is a humanoid robot, it does have 2 useless limbs. It is a good example of a reflexive robot. So it is in a dynamic environment. The packages are constantly moving, and it's reacting to the environment around it. So it couldn't pick up that bag, but it tried again in like a different orientation, picked it up. It flips the bags upside down. So this is like an example of a reflexive robot. Yeah.
Yes, automation at the macro level, which is this, versus, I'm sorry, the micro level versus the macro level at the enterprise. So it's disruptive to replace people with machines. What's the thought behind the people being displaced? And so now the people are displaced, you can't buy those things. Okay? And so robots don't buy stuff.
Yeah.
I'm serious, they don't buy stuff.
Yeah.
And so then if you constantly disrupt the natural order of humanity in terms of you work and you consume things. So if people are not working, then they can't buy things to consume. They don't have money, they don't have jobs.
Yeah.
And so there's something that has to be done at a higher level in terms of what happens to people when they have no work to do. Who's going to buy the cars? Who's going to buy stuff that these robots are producing?
Well, I think that's part of a bigger conversation about how we interact with technology as it advances, and what an industrial revolution really looks like. Because I do think that's what we're seeing kind of play out in this space right now. What I can tell you from experience is that I think there's a lot of concern about robotics replacing humans. And what we see actually more often in practice is robots helping and augmenting and kind of assisting humans to do those tasks, right? And so even if it is a job that was previously done by a human, the human that used to do that job is still working at that company. They're just doing something slightly different. The example that I like to use is we have a robot called the PaintBot that we put to work painting architectural signs in New Jersey. And the man that used to paint these signs, Gio, is a good friend. We got to know him very well. We're actually able to use all of his expertise to help program and train the robot. Now, Gio still works at the architectural signage company. His job has just shifted out of the hazardous environment of the paint booth and into the control center, where he's helping monitor the robot in real time. He's helping define new programs for the robot and expand its capabilities.
So take the analogy. So Amazon replaces people in terms of warehouse with a machine. So those people who scan around devices, robot, help the robot become better.
Normally, we don't look at it as a replacement. We look at it as an addition. And so it's the folks that are there are still, providing value, still working for the company, and still doing things. Oftentimes, just different things that involve less monotony and are less hazardous. And so, the jobs that robots are doing are jobs that we might make an argument that humans shouldn't be doing in the first place. Now, I will tell you that this is an hour-long video, so you get to see all the nitty-gritty details of how it actually works in the real world. It's super interesting. Watch it on 2x speed and have a good afternoon. But there's one more that I'd like to show you. And that's this idea of how do we actually train the robot to have new skills. This is one that we recorded in our lab yesterday. It's a technology that we're really excited about because it allows, back to that kind of human-robot connection, it removes the barrier for humans to interact with and communicate and work alongside robots. And so in this case, what we're doing is basically using a teaching device very similar to this guy that we have here, but specialized and augmented for painting. And what you saw is basically the person moving through and defining a few points that we wanted to paint on the helmet. Then the robot comes through and exactly replicates those points. And so, it really kind of showcases how we can add new capabilities to the robot without actually writing a single line of code. So with that being said, are there any other questions? I know I can see them looking at us to squeeze out of the room, yeah.
How far are we or are you from the state where you can generalize all those skills, like pick a coffee mug and put it on somewhere? So are we far from a library where you have 20,000 of the different activities and basically use them as a Lego? I buy a robot and I say, okay, pick a coffee mug, put it there, find a pitcher, pour a coffee and give me the mug, and I just give 3 instructions? Or do I have to train myself, my own robot in my environment, in my light, to do all those things, and only then it will repeat it? Can you generalize it?
So actually, Figure in that demo where they were putting up the groceries, they kind of are doing that already. So they have a generalized robot task, like a database, I'd say. So that's why it's able to deal with all those different items in real time like that. So it uses something called like a visual language action model. So it's been trained on, so the robot takes commands. So we tell the robot, okay, pick up this cardboard box and place it on this high shelf. So then someone will be programming the robot to like pick up this box, place it on a high shelf. So now it associates that voice command with that action. And then when you deploy it, it's a generalized program. So when it saw that ketchup bottle, it's never seen that ketchup bottle before, but it knows it's in the shape of like the cardboard box, for example, that it's been trained on. So it'll pick it up the same way it picked up that box, and it placed it in the refrigerator. It's never seen a refrigerator before, but it knows what a high shelf, like where it's supposed to be. So it places it there. So with VLAs, these generalized action models are being developed already. Yeah.
I would add to that though that one of the things that we're seeing in the open source community is exactly what you're talking about, which is kind of this modular library of skills that can be deployed across a variety of different robots. We're still at a point where a lot of that is dependent on the exact robot type. For example, you might not want to deploy the same skill set to a 6-axis robot that you would to a 4-axis robot or a 5-axis robot. So there's still a little bit of nuance there, but as the industry is standardizing a little bit more, that's definitely a trend that we're seeing. But I will say there's still an important role for the individual user to define exactly how they want that robot to act. For example, we might have a general model that identifies a bottle of ketchup and is able to place it in the refrigerator, but you might still want the ability to say, well, I want it on this shelf, not that one, right? And so there's still this kind of very important piece of human involvement to govern the logic that actually dictates what the robot does. Yeah.
Say going back to the senses, there's a big trend in air quality and gas detection. Like some places by law have to monitor for CO2, so it might not be smell as far as like we think of, but I've seen things argued as like digital notes and stuff like that. But it's more like parts per million. So it's not exactly.
Yeah. There's some really exciting things actually happening in that regard here in the Triangle. There's a really incredible company called Neura Inc., not to be confused with Neuralink, although it tripped me up the first time. But they're actually, oddly enough, a printing company that creates molecules that are able to be reactive to different chemicals or compounds in real time. Now, I have to tell you, the science is a little bit over my head, so I would encourage you to check them out. But the end goal and the vision for the technology that they're working on at NC State is basically a strip of fabric or cloth or tape that you might, for example, tape all the way around the ceiling of a room that detects CO2 and then transmits that information to a robotic interface. One of the exciting applications that we've seen is in fire detection, for example, that Neura Inc. is working on. Which is basically our traditional approach to fire detection is to detect smoke. What they're doing is actually being able to detect the temperature inside of batteries for electric vehicles and things like that, so that they can determine when a combustion is likely to happen up to 30 minutes before it actually does, which is huge in terms of prevention as opposed to curing. Is that our cue? Yeah. Yeah. Oh, I appreciate it.